So I'll kind of remind us what we were doing last class was comparing two sample means. We're looking at the difference between two sample means. So we kind of said we could think about this as, this is like our sample difference, right? Just kind of like we had the sample proportion, here's our sample difference. So we'll base our confidence interval around whatever that sample difference we see. And we then want a certain number of standard deviations away to get our lower and upper bound, depending on the confidence level that we wanted. We then multiplied that by the standard deviation for the difference in our sample means, okay? Which we said was simply take the variance of each sample mean, which was the variance of the data we sampled from over our sample size, and add those together for the two groups. So hopefully this is looking familiar. Right? This is some of the stuff that we did on Monday. Okay. So now we're going to just be looking at the difference in sample proportions. Okay. Just like with one population, if we're using proportions, we still get to use that standard normal distribution. Okay. Now here's where we don't really know this yet, but we can probably piece it together from what we know about the two sample means, right? The difference in sample mean example, as well as, if you recall, the variance of our sample proportions, we said was, the population proportion times 1 minus that over our sample size. If we didn't have the population proportion, we used our sample to estimate it. So we'll have this existing for both groups. And just like up here, where we added the variance of each sample mean together to get the variance for the difference in sample means, we're going to simply do the same exact thing for our proportions, where we take the variance of the sample proportions from group 1 and add that to the variance for the sample proportions from group 2. Well, that gives us our total variance, or our variance for the difference. We wanted the standard deviation, so we then take the square root. So it's really following the same set of rules, right? We're taking that sample difference, we're going a certain number of standard deviations away. It's just that to calculate the standard deviation for the difference in sample proportions, we have a slightly different formula now. Okay? So we piece that together. We ended up with this. Right? Oh, I'm gonna make it a little bit easier on you if you're copying this down. Got the exact same thing. The screen wants to cooperate. There we go. Sometime today, right? Oh, is it flashing for you guys too? Yeah. Let me try this and see if this fixes it. Try one more time. I think it doesn't like the presenter mode. Yeah, it doesn't like the presenter mode. So I'll walk through these kind of not in presenter mode here, because I think that it's screwing with the HTML or something's going on with the video. So there's our confidence interval equation, right? We kind of piece it together from things that we already knew. Really the same principles are going to apply. We're going to look that Z value up the same exact way. We're going to be given the sample proportions and sample sizes. So it's really just a matter of plugging things in to get this known equation. Right? So it's the same steps as we did with one population. We just have twice as, two of everything, two sample proportions, two sample sizes, and makes us gives a little bit more work to do, but nothing terribly brand new. So let's say I had something like this. So I've got 84% of people in 2011 supported healthcare coverage for everyone. And there was 607 people that were asked. In 2010, only 82% favored it, where we had a sample size of 600. Okay. So let's say I wanted to build the 99% confidence interval from the years 2011 to 2010. Okay. So what I'm thinking about here there we go, is I've got a newer time period and an older time period, right? So anytime we kind of have these examples where I'm comparing across time, we always want to put our newest time first. So I'm thinking about building my confidence interval around 2011 minus 2010's sample proportion. So all I'm doing is plugging my values in here, right? Where my group 1 is 2011 and my group 2 was the year 2010. So we'll blow this up here for a second so we can kind of see this. From there, it's just a matter of plugging everything in that we know. So my sample proportion from group 1 was 0.84 times 1 minus 0.84 over the sample size, which if I remember correctly was 607. I didn't leave myself enough room, so we're going to add to that, right? The sample proportion from group 2 times 1 minus that sample proportion from group 2 over group 2's sample size. So hopefully you left yourself a little more room than I did. And really at this point, the only thing left that we need is that Z value. So if I wanted the 99% confidence level, my alpha value is what? Remember, alpha is just the area outside my interval in decimal form. So the 99% level, alpha is 0.01. I then divide that by 2. So my alpha over 2 value is going to be 0.005, right? 0.01 over 2. So I'll go to my standard normal table. Right? I could look up 0.01. So scroll down here. Looks like it's actually, I shouldn't be looking up 0.01, right? Remember, I need to divide it by 2. So I was actually looking up 0.005. So I go back through, okay, where's 0.005? Looks like it's in between these two values. Right? It's as close as I can get. So negative 2.57, in between negative 2.57 and negative 2.58. Now, if you remember with confidence intervals, the number of standard deviations above and below, those signs are already built in. So I can look up alpha over 2, but because that is always going to be a small value, it's always going to be looking at that left tail. I'll always have a negative value there if I use the Z table. And then I just need to remember, okay, that's the value I want. I need to subtract that value to get my lower bound and add that number of standard deviations to get my upper bound. So negative 2.58, really what I'm plugging in here is just the absolute value of that because those signs are already in my confidence interval equation. So here I've got my 2.58. And really at that point, this is just a matter of computation. Plugged everything in. I've just got to get this entered in my calculator. Maybe it makes sense to calculate this first, right? And then I can plug that in, just kind of break it down to steps so I don't have to have as many parentheses in my calculator. Right? Now, another way I could have found that Z value, and I think this way makes a little more sense, but you know, everyone's different. If I go to that student T table and I find the column that has the area I want in the tail, and I just remember the very last row gives me the same values I would find from the standard normal distribution, right? So 0.005, if that's the area I want in the tail, 2.576. So it not only identifies what the value we needed was, right, but it does it a little bit more accurately, right? It can do it out to that third decimal. Right? We're not constrained to 2 decimals there if we use that last row of the student T table to find those standard normal or those Z values. Okay? So either process is fine. Both of them will get you the correct answer, at least rounded to the second decimal. So it's kind of, if you can remember that with the student T table, I think that's a little bit easier, but I understand if it's a little bit confusing. Why am I looking at my Z value on the T table? Well, that's just because I had kind of that last row as a comparison kind of row for you. Okay. Any questions over any of the procedure here? I've got one more confidence interval example. We'll probably go through a little bit quicker. So if there's any questions at this point, I'm going to stop and make sure. Okay. All right, so I'm scared to try this in presenter mode because I don't want to screw this up again and waste time. But right, we plug everything in. Once we get this entered into our calculator, we get this range of values, right? So negative 0.036 to 0.076. So let's think about here. Remember, I was doing 2011 minus 2010. So I was thinking about what's the true difference between 2011 proportion and 2010's proportion of people who favored healthcare coverage for everyone. I then found my upper and lower bound, right? So negative 0.036 and 0.076. So with 99% certainty, right, we built a 99% confidence interval. The true difference between these proportions is somewhere in this range. So what can I say has happened to the proportion of people who favored healthcare coverage for everyone? Can't really say much, because that difference could be positive, which would imply 2011, there was more favorable views of healthcare coverage for everyone. It could be a negative value, which would imply that 2010, there was actually a higher proportion. Or it could be that that difference, one of the possible values at the 99% level is 0. So if that true difference was 0, that would mean that these proportions haven't changed at all. They're exactly the same across those 2 years. So based off the sample evidence I found, I did see that there was a positive difference, right? I think it was like 0.02, 0.84 minus 0.82. But it would have been very likely, right? Even if that true difference was 0, it's not very unlikely that the difference I see in my sample proportions was something like 0.02, right? And so, when I created this range of values, sure enough, I mean, this value, this range is pretty big. It includes differences that are positive, negative, and even that true difference could be 0. So I can't really say much here at the 99% level. Okay. Now, if I only had positive or if I only had negative values, then I can, make some interesting statements about 1 year. It was more in favor of healthcare coverage for everyone, compared to the other, or vice versa. So I had this other confidence interval example that I just thought was kind of interesting. It's some different numbers, maybe some good practice on your own. We could walk through this. It's going to be very, very similar, right? I've got 2 time periods. I've got the same sample sizes. I've got 2 different sample proportions. So 0.51, 51% of people had unfavorable views of the Affordable Health Care Act in Indiana for 2011. And in 2010, only 48% of people had an unfavorable view. So my proportions would be 0.51 and 0.48. So the sample difference I found here, right? If I'm thinking about the difference that I saw in my sample proportions now, 0.51 minus 0.48. So it should be centered around 0.03. I would then go, determine what my margin of error is. I would look up that Z value that gives me alpha over 2 in the tail. But if I'm still building the 99% confidence interval, what's that Z value going to be? You don't remember the exact number. We built a 99% confidence interval here. If I'm using the standard normal distribution, the Z value at the 99% confidence interval, if I'm building a 99% confidence interval, it's always going to be the same value. If I go look up alpha of 0.01 divided by 2, I look at 0.005, I'm always going to find the exact same number from that standard normal distribution. So I would have the exact same Z values we had before. And from there, it's just a matter of plugging in our sample proportion for group 1, the sample size from group 1, sample proportion for group 2, sample size from group 2. We subtract our margin of error to get our lower bound. We add the margin of error to get our upper bound. And now I've got my confidence interval for the change in views of the Affordable Health Care Act between these 2 years. So same, really, really similar process. It's just, slightly different values here. Okay. Any questions kind of over anything here with the confidence intervals? So one thing that's interesting to point out here with this example, so this was an actual survey. And we could actually probably run through the numbers if we really wanted to say not necessarily was there a change over time, but was there a difference in the proportion of people, let's say in 2011, that, here, let me see. So was there a difference? Oh, in 2011 for the proportion of people who, we'll call this healthcare coverage for everyone, and people who had unfavorable views of the Affordable Health Care Act. So I think if I remember the 2011 numbers right, this was 0.84 and 0.51. So here we see a pretty large sample difference, right? So this is like 0.33. So here I've got pretty strong evidence that there's differences in how people view the Affordable Health Care Act and whether or not they support healthcare coverage for everyone. But the interesting thing here is that that difference really should be zero. I mean, the Affordable Health Care Act, right, had other things in it other than healthcare coverage for everyone, but that was basically its main point. Right? That was the thing that it was trying to get done. So it's interesting when you phrase a question. This is kind of goes back to when we were talking about biases. Notice that when they ask people about the actual issue, do you think everyone should have healthcare coverage, or we should kind of ensure healthcare coverage for everyone? Wildly popular viewpoint. 84% of people say yes. When you ask them about the act that tries to get this thing established, about 50-50 split, right? So kind of an interesting point about how you phrase questions, and right, really trying to get at what people's views are. You want to kind of stay away from like any kind of political, labeling of political policies or things like that. You really just want to kind of try to strip it of any connotations or anything that it could have. So kind of an interesting example there from that survey. So the next thing that we're going to move on to, let's see if this screws up, because I didn't mean to hit that. I did it out of habit. So we'll see if this screws up on us again. So, we had these sample variances for each proportion. And when we wanted to do hypothesis testing, we have a small problem, okay? So we'll go by stop share here, and we'll try to kind of think about, for hypothesis testing for the difference in two proportions, it's going to look identical to what we did on Monday for sample means, with one small difference. The test statistic equation is going to look a little different. So when we had the test statistic for the difference in sample means, we took that difference in the two groups sample means, right? We said technically we're subtracting the assumed true difference, but I'm always going to keep this as zero, right? I was going to kind of simplify that and always keep that as zero. We then divided by our standard deviation of that statistic we were interested in, which is now the difference in sample means. Okay? So this looks something like this. Not two, this is N1 and N2. We're going to have one issue if we try to do a similar thing for confidence intervals. So for hypothesis testing with proportions. So based off of our confidence interval, we might think that we already have that standard deviation for the difference in our sample proportions. The issue is, if we recall what we did with one population for a proportion here, we took the sample proportion, subtracted the assumed true proportion, divided by the assumed true proportion times 1 minus the sample proportion over the sample size. So now, however, we don't have an assumed true proportion, right? All we have is an assumed true difference, right? So if I'm thinking about trying to do this for a two population proportion example, the problem is, let's say I have this assumed true difference of 0. My actual sample proportions, or actually, even if they weren't sample proportions, what this could imply is that the true proportions from group 1 and group 2, right? If this is equal to 0, they could both be 0.2, they could both be 0.4, they could both be 0.392, right? This difference could be 0, even though those proportions are different values. Okay? So in order for us to have a test statistic that comes from a standard normal distribution, and this is one of those, we could Google the proof and it's kind of nasty. But what ends up being true is we have a slightly different equation for that test statistic, which is going to look something like this. So we have to break it down to parts this time. I mean, we don't have to, but I did because I think it's a little bit easier. So we're first going to find this P bar, which really all we're doing there is plugging in our sample sizes, our sample proportion. It's essentially giving us kind of like this weighted value between our two proportions. We're then going to take that p-bar and plug it in to our denominator, plug in our sample sizes, plug in our sample portions, and now it's just a matter of computation. Now you could do this all on one line, right? I could just write out, plug in p-bar here, plug in p-bar there. It just makes the equation a lot longer, a lot more parentheses would be needed. And so usually, I think the easier way to do this is to first find this p-bar, then plug that value in, kind of breaking it down into steps here. Okay. But it still represents, this is still representing the standard deviation of the difference in my sample proportion. It just accounts for the fact that if I've got an assumed true difference of 0, these proportions could be anything. They could both be 0.1, they could both be 0.3, they could both be 0.159, right? And so I'm gonna have to, in order to ensure that this is a test statistic, I have to calculate that. It's almost like we have an assumed true standard deviation there. Okay. And don't worry about these. I'll never kind of make sure that these are broken, just kind of out of the sake of being complete, right? We have to have sample size kind of proportion of, or using the proportion of the sample size, we need to make sure that they're above certain values. Here, just need to make sure they're greater than 5, right? This ensures that if something's very, very unlikely, then we would need a higher sample size to be able to pick up from our sample what that proportion actually is. Like if we were dealing with something where it was like 1 out of 10,000 or something like that. But we don't have to worry about that. So we've got our test statistical equation. Once we have that, the steps are identical to what we did before. Same thing that we did on Monday. Okay? So we'll work through a couple problems and then we'll kind of take a dive into Excel. Okay? So I had some old polling data from before the last election. I think Rasmussen was the company that got the 2016 election correct. And they wanted to try to predict the 2020. So they had 1,500 likely voters. They found a sample proportion of people who are going to vote for Biden to be 0.49. Sample proportion of people who are going to vote for Trump was 0.47. So pretty high sample size, right? So you would think we'd be able to maybe make a rejection decision here, right? If we find a difference, which we did, right? There's what's that sample difference that we found? We kind of think about the proportion of people voting for Biden minus proportion voting for Trump. Our sample proportions we found were 0.49 and 0.47. So we kind of see this sample difference of 0.02. Zoom in a little bit here. I don't know. Do you guys like the board better or do you like this document? I don't know. Anyone have any opinions? Do you like this a bit? The only thing, so I like this a little bit in that I can like constantly point between things on here and things on the slide and kind of line up my work a little bit better. But I'll probably poll you here at some point about which you like more and then kind of end the semester using whichever one kind of wins out. But I wanted to try this for a little bit. So that's just kind of where we're starting out, just to think about this problem. But the very first question we're asked is, let's assume I want to test for whether or not Trump is going to get more votes than Biden here. Or actually, how did I phrase it? I want to test for whether or not Biden will receive more votes than Trump. Sorry, Biden more votes than Trump. So I want to test for whether or not the proportion of people who are voting for Biden versus Trump is larger. So if that's what I want to test for, what I'm really saying is that difference greater than 0? Because if I'm wanting to test for that, the proportion of voters for Biden is greater than Trump, the only way that's possible is if that difference is above 0. So that's what I want to test for. That's my alternative hypothesis. I assume the opposite is true, which is that true difference is less than or equal to 0. Okay. Now, so we've got A here, right? But I'm telling you, anytime you have these two population examples, I'm always using the assumed true difference of 0. So sometimes it'll be greater than 0, less than 0, or not equal to 0, but I'm always using that assumed true difference of 0. Okay. So B and C should have even entered our minds here, right? I should have that assumed true difference of 0. Now from here, all right, I could calculate my test statistic, or I first could find my critical value. Okay. So I'm going to skip ahead and first find our test statistic and then come back and we'll do critical value. Okay. So if I wanted to find my test statistic, right, let's think about what I'm doing. So I've got this assumed true difference of 0. And I know that if that is in fact the true difference, then the difference in my sample proportions will be normally distributed around it, right? Centered around it. Okay. I saw this sample difference of 0.02. So the next step that I'm going to do is, well, I've got proportions, so I know that I can turn this into a test statistic coming from a standard normal distribution or a Z statistic. So that's my next step, right? Once I have that Z statistic, it's a what type of tailed test? Right tailed test. So my p-value is the probability I see that test statistic or anything to the right of it. Okay. So from here, it's just a matter of kind of using, we'll have that formula sheet, and I'll try to get that up here toward either tomorrow or Friday, well in advance of the final. But you can start taking a look and seeing what that formula sheet's going to look like. And one of the formulas I'll give you there is going to be, I'm going to try to minimize this here. This guy right here, right? So here's our test statistical equation when we have two sample proportions. We said we can break it down, do the intermediate steps. So plug in my sample sizes here of 1,500 people who are voting, plug in my sample proportions of 0.49 and 0.47. Notice this one, because the sample sizes are the same, it's really just giving me kind of a weighted average here, right? So 0.48, plug that into P bar, plug in my sample size of 1,500, my sample proportions, my assumed true difference is 0. Right? This is kind of a matter of identifying, I've got two proportions. I want the test statistic, so here's my equation, right? Where I'm looking at the statistic I'm interested in, subtract the assumed true value of that statistic, and divide by the standard deviation of that statistic. So once I do that, I've got this test statistic value of 1.097. Okay. Well, that's great, but I can't make my rejection decision based off of that. So the next thing that I might want to do is use that test statistic to find my p-value. Okay. So I had what, 1.097, I think was the test statistic there. So what I can do is look that value up in my standard normal table. Now the table is going to give me the area to the left. I had a right tailed test. I wanted the area to the right. So I'm going to have to do what? Yeah, take this value and subtract it from 1. Right? So 1.097, I guess that rounds to 1.1, right? 1.10. I'm rounding to the second decimal there. So I go to my standard normal table. I know the Z value, right? I have my test statistic is a Z value. So 1.1, you got to scroll down here, 1.10, 0.8643. Right? So 0.8643. Okay. So I subtract that from 1, and my p-value, there we go. So 0.8643, subtract that from 1. So my p-value is what? 0.1357. So what levels can I reject the null at here? How do we make our rejection decision? If the p-value is, yeah, none of them, because we only reject if it's less than alpha. For my 3 benchmark alpha values, I'm not less than any of them, right? So I would say I failed to reject at all levels, okay? So the rejection decision is exactly the same way we're doing with one population, right? Just compare the p-value to alpha. If the probability of seeing what we did isn't low enough, then we fail to reject what we assume to be true, right? We assume the difference is 0. It ended up being we saw a sample difference where the probability of seeing that sample difference, if in fact what we assume to be true was true, that probability was only like 13%. And the threshold values that we usually set as cutoffs are we only reject if what we saw, if it was unlikely enough to have a probability that's below either what, 10, 5, or 1%, or a probability of 0.1, 0.05, or 0.01. Okay. Any questions over anything there before we keep moving? Okay with this? Hopefully hypothesis testing is starting to sink in what we're doing here. What we're really doing is looking at the sample evidence we found and saying, how inconsistent is it with what I assume to be true? If it becomes inconsistent enough, right, the probability of seeing it gets below a certain level, then I'm okay saying what I assume to be true is probably wrong. If it doesn't get below those levels, then I don't have strong evidence that goes against my natural or my original assumption. I shouldn't say natural, my original assumption. So here we didn't find strong enough evidence. Now we could have also done the critical value approach here. Right. So the critical value approach, actually, I'll use blue still, would be, okay, look up and find the critical value that gives you your desired alpha, and we'll just do 0.1 here. Actually, I think the slides say 0.01, so let's try to line up with those. So if I want to find the critical value at the 99% level or the 1% significance level or 99% confidence level, so 0.01, for a right-tailed test, I know that means my critical value is going to be what? Not the specific value, but if it's a right-tailed test, my critical values are positive. Left-tailed test, they're negative. Two-tailed test, I'll have a pair, right? So that pair would give me kind of alpha over 2 in each tail. So I'll go to my table. I could use the standard normal, right? So I come down here. I'm going to look for 0.01. Oh, why am I not seeing it? Here we go. In between these two. So negative 2.32 and negative 2.33. So we'll use the higher of the two. However, if I look up alpha, that's always going to be looking at the left side of this distribution. So it's going to give me the value I want, but I had a right-tailed test. So because it's symmetric, it's going to be that same value, but positive. Right? So my critical value here we just found was 2.33. For a right-tailed test, my rejection region is the area to the right of that. Where would my test statistic fall? If we go back, my test statistic was 1.097. It's going to be like somewhere down here. Right? So pretty far from my rejection region, right? That test statistic is pretty far below. I don't know why I put the number up here. 1.097. Right? Pretty far from being in that rejection region. So we failed to reject at the 99% level, which we already said using the p-value, we failed to reject at any level, right? Okay. Any questions on this? All right. So let's go back here. Let's test our luck one more time with this viewer. So let's say we go back and we want to look at that healthcare coverage, and we already did a confidence interval for it, but let's try to do a hypothesis test as well, right? Now, we'll see if they line up, because here I just want to test for whether or not views are any different between the 2 years. So really what I'm saying there is, if the proportions are different from 2011 to 2010, that would just mean that their difference would be any other value except for 0. Right? So if I want to test for whether or not proportions are different, right, I'm saying, is that difference anything other than 0? I'll assume the opposite is true, stack the deck against myself, and assume that it's exactly equal to 0. Okay, so I've got a two-tailed test here. Right? Now, if we go back to the confidence interval, oh, I had it somewhere here, so let's see if I can find it. If we go back to that confidence interval, oh, did I actually find the? Oh, I know that. Oh, here it was. Right? We had this kind of as the range. So one of those values in that confidence interval was 0. So what we were saying was any value in here could be the true difference between 2011 and 2010. So when we go to do this hypothesis test, if we're testing against this value of 0, the confidence interval already kind of alludes to the fact that we probably should fail to reject it, right? 0 was one of the values that was in that confidence interval. So we can go through the process and hopefully our hypothesis test lines up with what we're doing with the confidence interval. Okay? So the first thing that I would kind of ask you to do is to find the critical value. So I'm hoping that we're all on the same page here. So I'm going to ask you this one as kind of this eye clicker question. If I was looking for the difference in these sample proportions, right? I don't want the test statistic here. I'm saying, well, how would you find the critical value? Okay. So the critical value is going to give you alpha total in the tails, right? Remember, we have a two-tailed test now, so alpha total in the tails, which means you'd have alpha divided by 2 in each tail. So hopefully you've got the table in front of you, or you can pull it open up on your phone, or I'll even give you, yeah. Oh, is it not coming up on the reef? Here, let me see. Let's exit out of it. Okay, it says enabled. Let's try one more time. It's showing up now? Okay, so one thing that also, if you don't have the tables in front of you, if you actually look carefully at this one, remember in the previous problem, we had a right tail test. I wanted the critical value at the 1% significance level, right? And that led to having a critical value of 2.33. So here I've got a two-tail test, which means instead of having alpha in the tail, I'm going to have alpha over 2 in each tail. So think about what would have to be true about my critical value relative to the problem we just did in order to get only half of alpha in each tail. Okay. So give you a little bit of time to think about that one, kind of look up that critical value if you actually want to just go through the process and look it up on your Z table. And then we'll kind of talk about it here in about a minute. So we're looking at that 99% confidence or the 1% significance level. Like I said, even if you don't have that table, you think about relative to the problem we just worked through, what would have to be true about the critical value, because we're keeping the level the same, alpha is still going to be the same 0.01. What would have to be true about the value in order to get alpha over 2 in each tail? All right, you haven't gotten an answer in, take your best guess here. Got 21 of us here today, 23. Everybody got their answer in? I'm gonna close it out. All right. So what does the answer have to be here, even if you didn't have the table? A, right? So first of all, I wasn't kind in the sense that I gave you pairs of critical values for all the possible answers, right? You know, for a two-tailed test, right, which I kind of repeatedly said we had here, that we're going to have alpha over 2 in each tail. So that means we need a critical value on the left and a critical value on the right. So think about what we had in the previous problem. We said that the critical value, or the Z value here, that gave us an area of 0.01 in that tail was 2.33. So if I now want alpha over 2, right, in each tail, or 0.005, right, 0.01 divided by 2, what has to be true about the critical value that would give me that 0.005 in that upper right tail? Has to be greater, right? There's only one answer of these four that was greater, and that was the 2.576. Is that clear how just from kind of knowing the principles behind what I'm doing here, right? If I want a smaller area in this tail, I need to go out a further number of standard deviations, right? Going from a 1 to a 2-tailed test, instead of wanting alpha in the tail, I wanted alpha over 2 in each tail, right? Okay. Now, if I wasn't as kind with the options I gave you, you would actually have to go through. You could use either the Z tables or the last row of that T table. I think that's what I actually did since I had it out to 3 decimals. So if I go up here and think about the area I wanted in each tail was 0.005. I then scroll down to my very last row, which I know gives me my standard normal values. And that gave me the 2.576. And then I remember, oh yeah, it's a 2-tailed test. So evidence on either side, right, would go against the null. So I have like a rejection region on either side of that distribution. Okay. Any questions here before we keep moving? So if I've got my critical values, what's probably the easiest approach to use is the critical value approach. So without having the numbers, what's the next thing that I need to do? Calculate my, what do I compare to the critical values? You don't have any idea? Yeah, I calculate my test statistic. I'm okay with awkward silences. So answer if I'm waiting for a while. It means I want someone to kind of, I want to see, make sure you guys are kind of follow along with me. So I'm going to have to determine where my test statistic is and see if it falls in my rejection region or if it doesn't. Okay. So here, right, we're just going to go back to, oops. We've got that information given to us, right? So we can have our sample proportions, our sample sizes. That's really all we need to calculate the test statistic for 2 sample proportions, right? So I look here, that's all I need are the 2 sample sizes, 2 sample proportions. I can calculate that P bar, right? The intermediate step here. So plug in 0.84, 0.82, 607, 600. I get about 0.83, plug that in for my P bar value. Plug in my sample size and my sample proportion. This is just really an exercise in kind of being able to plug our values in where they fit. Right? And the notation is kind of given to us a lot of the time. So like we know the sample proportions, we know the sample sizes, right? And we're just plugging them in kind of where they go. Okay. So like I said, these maybe an easy thing to do to prevent from calculator mistakes is like, so first find P bar, plug that in. Find the denominator, maybe then take the difference and divide it by whatever number you found for the denominator. Because as we kind of, try to enter this all at one time, you're going to have a lot of parentheses. It's easy to forget one. So I would kind of suggest breaking it down into parts as much as you can. Okay. Any questions on this one before we keep moving? So if I look at that test statistic, this one's actually pretty easy, right? If I plot this against my critical values, right, 0.9 is going to be somewhere down here. So my test statistic isn't anywhere close to my rejection region. Or think about this differently. What I was really doing with my critical values was saying, look, 2.576, if I see sample evidence that's any more than 2.576 standard deviations away from that assumed true value, I'm okay rejecting. So what I'm really saying is if the absolute value of that test statistic is greater than this threshold number of standard deviations away I set, because that's all the Z value or the Z statistic's telling me. It's the number of standard deviations away my sample evidence was from that assumed true difference. So anytime, the absolute value of my test statistic is larger than my critical value, I reject. Well, very clearly here, 0.9 is not less than 2.576. So that doesn't hold. So here we would say I fail to reject. I think this corresponded to what the alpha over 2, so the 1% significance level or the 99% confidence level. Now, what these proportion examples point out is it's very hard to be able to reject the null when we're looking at the difference in sample proportions. So part of the reason why is, I mean, we just typically don't see very large differences, right? What's the largest difference we could see between two sample proportions? If one sample proportion was 1, the other one was 0, the largest difference we're ever going to see is 1, right? So even if we get really high sample sizes, 600, 607, the other one we had 1,500, it's just very hard to find something that's enough standard deviations away, right, that we can reject them. Now we can, I think the example I've got in Excel here in a second, we'll actually end up with a hypothesis test where we can start to see something that gets close to where we can reject. But it is very hard to reject the null hypothesis for the difference between two sample proportions if we're doing this, at our kind of benchmark levels of 90, 95, 99% confidence levels. Okay. I think that's the last thing I have there. Yeah. So there's one more thing I wanted to point out before we go to Excel, and now, I know what it was. Okay. So I just said that it's really hard to reject, right, with these proportions. So I'm going to write out that test statistic equation, and we're going to think about something that I think this was a problem on one of the practice exams that I forgot to take off, but I didn't ask you on the exam because it was something we didn't cover. So P bar times 1 minus P bar times 1 over the sample size from group 1, 1 over the sample size from group 2. Okay. What happens if I find the same sample difference? So let's assume that this sample difference I find doesn't change at all, but I was able to take higher sample sizes. So let's say my sample sizes go up, right? So my sample sizes increase, right? But I still find the same sample proportions, or that same sample difference. What's going to happen to my denominator here? Well, if these two values go up, 1 over a larger value, it's actually going to get smaller. Right? What does my denominator represent? The standard deviation for the difference in those sample proportions. So higher sample sizes will drive my standard deviation or my variance for that difference down. If my denominator is getting smaller, what happens to my test statistic? Yeah, it goes up, right? Because now I found the same sample difference. But if the standard deviation is smaller, it's going to be a higher number of standard deviations away, right? 0.02 is only one standard deviation above the assumed true value of 0 if my standard deviation is 0.02. But it's 2 standard deviations above if my standard deviation is 0.01. So seeing that same sample difference, but a smaller standard deviation means I'm a higher number of standard deviations away, or my test statistic is larger. If my test statistic gets larger, what happens to my p-value? My test statistic's getting larger. Let's assume it's a right-tailed test. My test statistic gets larger. What's happening to the p-value? For the area in that tail, it's getting smaller, right? If my p-value is smaller, is it more or less likely that I can reject the null? Well, remember, we only reject if the p-value is less than alpha. So if my p-value is getting smaller, it's going to be more likely that it's below alpha, right? Whatever alpha I set. So you can walk through this with every single type of example we work through. Anytime we get higher sample sizes, it decreases the standard deviation of that test statistic, which increases it decreases the standard deviation of the sample statistic we're looking at, which increases the test statistic, decreasing the p-value, making it more likely we can reject the null. So once again, I don't know if I've ever given you an example yet where having higher sample sizes is a bad thing. It's always better to have more data, right? because it makes it more likely we can kind of pin down where the true population values actually are. Okay. Any questions on this? Is this making sense here? All right. So now we get to do a little bit of work in Excel. So last class we left off and we were comparing the Southern and Midwest universities, right? So now I'm going to go back to this Midwest university data set, or worksheet, I should say. And I've got all these different universities. And what I did was, if they had more female than they did male students, I put a 1. If they had more male than female students, I put a 0. Okay. So this was like just a collection of D1 universities. So we found the mean enrollment. Now I want to find the sample proportion of schools that have more female than male students in the Midwest. Well, if I have a 1-0 variable and I want to find kind of the sample proportion, how can I do that? In Excel, or we said even by hand, that's simply finding the mean, all right? So if I found the mean of a 1-0 variable, basically it adds up all these values. So 1 plus 1 plus 1 plus 1 plus some zeros are in there, but the zeros don't change anything. So the numerator just counts the number of schools that have more females than males. And then in the second part of calculating mean, you add up all the numbers and then you divide by the total number of observations. So my mean is going to add up the number of ones, or the number of schools with more female students, and divide it by the total number of universities I have in this data set, which is basically my sample proportion, number of successes over the number of trials. So I'll find the mean of this 1-0 variable. Right? Remember, that's hold Control and Shift, or Command Shift on a Mac and the down arrow. We can use that count function for finding our sample size. Hopefully we're getting familiar with this. We've used it a lot at this point. So I've got about, what, 3/4 of the universities in my sample from the Midwest have more female than male students. This is pretty in line with like a lot of the growing, or a lot of the research showing the trends of undergraduate enrollment. So one thing I showed you last class, and I'll show it to you again because it's pretty useful. Did I harp on this about accounting majors, that this is useful on Monday? So if I didn't, if you're doing accounting and you want to go across all these things I forgot, your balance sheets and your income statements, I don't even know if that's one of them at this point. It's been so long since I had an accounting class. But, right, you want to cross-reference things on different sheets. So in the Midwest, right, I'll put equals and then select that Midwest worksheet. And I want to put the sample proportion I found on that Midwest kind of worksheet. And then it puts it there for me. Notice it kind of does this little go to the Midwest worksheet to cell P4. Right? Now I can also copy down and it'll keep the worksheet the same, but it'll just move down one on that Midwest. So notice I copied it down one because I knew that I had it set up on that other worksheet. So the sample size was right below the sample proportion. So that's kind of a nice little trick you can do, kind of copying with those cells references, updating. So we've got our sample portion and sample size from the Midwest. I now want to do the same thing for the South. So I'll find the sample mean for schools in the South that have more female than male students. Then I'll find my sample size using that count function. Now, these should all be things that we're pretty familiar with. Okay. So notice in the South, most Southern schools have more females enrolled than males, right? 85%. It's pretty high. Right? So if I want to start to do something like the difference in my sample proportions here, like the difference between Midwest and Southern schools in terms of their, proportion that have more female than male students. Excuse me. I'm going to break it up into steps and calculate that standard deviation for the difference in sample proportions in a different cell. Okay. I'm actually going to move this down because I know this is going to screw something up that I want to make sure you can see. So I'm going to take the square root of my first group sample proportion times 1 minus that group's sample proportion, right, divided by that group sample size. And then add to that my second group sample proportion times 1 minus that group's sample proportion divided by that group's sample size. To me, this is a lot easier than doing this by hand. If I had to like keep this out to 5 decimals or something, enter this into a calculator, worry about my parentheses, a little bit easier for me, I think, to do this in Excel. So we've got that standard deviation for the difference in our sample proportions. The only other things we need are the z values for different confidence intervals we might want to build, and then find that sample difference. All right. So I'm going to go down here. Well, actually, after I hit enter, and I've got that standard deviation for the difference in proportions. The z value, does anybody remember, if I know the area that I want on each side of my confidence interval, which is just alpha over 2, how can I look that value up in Excel? I know the area in the tail. I want to find the corresponding z value. So I'm working in, like I'm doing the inverse, right? So the function we have there is, well, I'm using proportions, so I'm using a standard normal distribution, but I'm working in reverse, or the inverse, right? And I want alpha divided by 2, right, in each side of my confidence interval. Now, if I hit enter here, the problem is going to be, it's always going to give me a negative value because it's dealing with that left side of the distribution. Well, I know that the positive and negative, right, the number of standard deviations above and below I want to go to get my lower and upper bound, that's already built into my confidence interval equation. Okay. So what I'm going to do here, just so I have the value, is do that ABS function. That just takes the absolute value. Now I can copy this down, and I've got that number of standard deviations the way I need to go for each of these 3 different levels of confidence. Okay. Now notice, we're using the standard normal distribution, so it's the exact same values as what we found on Monday for the difference in sample means. Right? It's the exact same thing if I had sample means and I knew the population variances, or if I'm dealing with proportions. Okay. So the next step is, we're just going to base our confidence interval around whatever the sample difference we found was. So we'll do the south. Whoops, what did I forget? Equal sign. Take the sample proportion from the south minus the sample proportion for the Midwest. That's my sample difference. I'm centering my confidence interval around that. That's the best guess I have about what the true difference is. I'm then going to subtract the number of standard deviations away I need to go to get my lower bound, and multiply that by, this is where it's kind of a nice shortcut. Instead of entering all this into this cell, I already did all that up here, right? I already found that standard deviation for the difference in my sample proportions. So I'm just going to click on that up there. Okay. So this should give me my lower bound. If I want to copy this down and get the lower bound for the next 2 confidence levels as well, what am I going to want to do here? The only thing that I want to change is what? Yeah, that z value. Okay. So everything else is going to be the exact same. So I'm going to go through, hit F4 or Command T on a Mac, freeze everything else. All right. So those cell references won't change when I copy this down. Now I'll copy this down real quick, and I've got my 3 lower bounds. Okay. Now to get my upper bounds, it's going to be this exact same equation. So I'll copy that using Control C as my shortcut there. It's probably Command C on a Mac if I had to guess. Go in over here, paste it. I'm adding my margin of error instead of subtracting it to get my upper bound. But really, once I hit that, I can copy this down. I've just built 3 confidence intervals relatively quickly. Okay. Any questions? I want to see one of those cells again, or kind of any questions on anything that we just did there. Okay with that? So what can I say about the proportion of schools in the South that have more females than males relative to those in the Midwest? I look at this confidence interval. What could I say about the relationship between those South and Midwest schools? Proportions here. Yeah, I can't say anything with these levels of confidence. So why? Because all of them include the value of 0, right? Notice the lower bound is negative, the upper bound is positive. So I can't really say that one is greater than the other. Now notice, I found a pretty big difference, like over 0.1 here. but my sample sizes weren't the largest. And so I really didn't have a strong enough evidence to be able to say that. Now, what is kind of interesting is, let's say I want to do it at the 85% confidence level. With 85% confidence, I could say that, Southern schools have a higher proportion of schools that have more female than male students, right? Because now my confidence interval only includes positive values. Okay. Any questions on the confidence interval stuff before we keep moving here? So we can do one more thing, which is hypothesis testing. Right? So we have that critical value. We have our test statistic equation that's a little bit new. So I'm looking here. Where did I have it? We had it on one of these. Oh, wrote it right here. Right. So there's no built-in function in Excel. We're just going to have to kind of use it to be our calculator. One of the things we needed was P bar here. So I don't think I have it on one of these worksheets, but all that was taking each group's, oh man, I don't want this to, I want you to be able to see everything. Let me move this up here for a second. Okay. So all I'm going to do is take each group sample proportion, multiply that by that group sample size, and then divided that by the sum of the two sample sizes. So this plus this. So there's my P bar. I'm then going to use that value for P bar and kind of just type in my test statistical equation here. So the numerator is take the South proportion minus the Midwest proportion. We don't have to do anything with that assumed true difference if we don't want to. I'll always give you the assumed true difference of 0. But here, I've got some hypothesized values here. So I'm just going to select the 0 that I know is down there. So that's my numerator. Divide that by the square root of P bar, which is what, in cell S13, times 1 minus P bar. And then multiply that by 1 over the sample size from group 1 plus 1 over sample size from group 2. Okay. So on these test statistics, I just have to use Excel to be my calculator. Okay. So I'm going to hit enter here, right? And I've got my test statistic. Now here, I think I had, let's set this up as a two-tailed test, right? So instead of like what I have here in the slide, let's see if I can get to, there he goes. Well, whatever. Can I delete this? No. All right, assume that this is our null hypothesis over here. That we had a difference be equal to 0, okay? So I'm gonna set this up like a two-tailed test, okay? So if I have a two-tailed test and I see this positive test statistic, I can find the area in that right tail, but then I have to remember I then need to multiply it by 2. It's a two-tailed test, okay? So I'll look up that test statistic. Let's say it's about 1.4. I can find the area to the right, but then I have to remember evidence on the other side would have went against the null as well. I need to multiply it by 2. So when I'm looking this value up, if I use that norm.s.dist, I tell it that z statistic, comma 1, that's going to give me the area to the left. I wanted the area to the right, so I need to do what? Subtract that from 1, okay? And then it's a two-tailed test, so whatever that area in that right tail is, I then need to multiply it by 2, because it would have been equally as likely for me to see sample evidence on the other side that went against the null as well, okay? So when we're looking up p-values, you use that norm.s.dist if you have proportions or sample means with known population variances, okay? So we get a pretty high p-value here, so we just barely fail to reject, right? It's not quite less than 0.1. Right? Now, if I had wanted to use the critical value approach, instead of using norm.s.dist, I'm working in the reverse, right? So norm.s.inv. However, I don't want all of alpha in my tail. I want alpha over 2 in each tail, right? So alpha over 2, right? That would give me only half of my critical value, right? So for a two-tailed test, I need to somehow indicate I've got 2 critical values, which here, if I take the absolute value, right next to it, now that kind of indicates that I've got both a positive and a negative critical value here. Okay. Any questions over anything here? You want to see a cell again? Okay. I guess it's good that I put up these videos. I'm feeling like a couple people aren't paying an ounce of attention to what I'm doing. So that's always good. But no, once we do work through all of these, I will kind of splice everything together so that you'll have the work we did in Excel. Also, I don't know. It's, there's a lot to keep track of. Right? We went through an example where we compared sample means and population variances on Monday. We're comparing sample proportions here today. On Monday's class, we'll basically go through, compare sample means, and we only have sample variances. It's going to look very similar, but right, if we only have sample variances, what do you think is probably going to change? We need to use, what did we have to do with one population examples? If I only had the sample variance, I need to use there's only one other distribution, the student T distributions, right? We only had sample variances. That was the situation where we said we had to use that student T distribution. So same thing with 2 population examples. If I only have sample variances for a sample mean where I'm comparing 2 sample means, I'm going to have to be using that student T distribution. So some of the stuff we did in Excel will change because I'm using that t.dist and t.inv function now. I'll show you some built-in shortcuts to finding the p-value pretty quickly for these 2 population examples. And then, once we get back from Thanksgiving, we'll basically be kind of start from basically linear regression, and that'll be like all we talk about for a week and a half, 2 weeks before we start doing some review for that final. Okay. So I had some people ask me about the final in terms of, is it comprehensive? So basically, it's going to be from where we left off in this last exam. So much smaller scope of topics, but it is kind of comprehensive in the sense that, we're doing hypothesis testing and confidence intervals again, and all of this is kind of building on what we did with one population, right? So we're kind of getting these same principles. So if we didn't do too well on those questions on that second exam, really strongly suggest kind of going back through and reviewing that, making sure you're trying to get a better understanding of that, because that's going to be a lot of this next exam. And then we're also going to have kind of about half of it be all that kind of newer linear regression stuff we start talking about. Okay? I'll get that 4th Excel assignment up there. I think I held off after Monday with some potential issues with the exam for someone that might still take it. And so I didn't post the answer key, but I'll post the answer key after today's class so you can start to go back through and review and figure out which ones you got wrong.
Are you gonna practice?
Yeah, I'll probably be pretty nice. I'll probably like the other 2. Like I'll probably have 2 or 3 of them. And it's kind of the same sort of setup. The practice exams will look pretty similar to what the final looks like. But yeah, you'll have a good batch of questions there. And my guess is I'll have those posted sometimes over Thanksgiving break. All right, I'll see you guys on